Hello. In this video, I'm going to explain how magma is created and how it can form igneous rocks with a wide range of compositions. So magma is created when heat from the inner earth melts the upper lithosphere. This magma is then forced towards the Earth's surface and results in volcanoes where magma erupts onto the surface. When magma is originally created, it's mafic, rich in iron and magnesium, but low in silicon. As it travels to the surface, the magma cools, which forms igneous rocks. This is how new Earth material is formed. Igneous rocks are not all the same, however. Some have the same mafic composition as the original magma, but others are felsic, which is rich in silicon, but low in iron and magnesium. This really depends on where the magma is created. There are three different areas in which it can be created. These are mid-ocean ridges, volcanic arcs, and hotspots. The majority of Earth's magma forms at plate boundaries where heat can easily reach the mantle through cracks. The two zones where magma is most commonly found are at mid-ocean ridges, where oceanic plates are being pulled apart, and at subduction zones, where an oceanic plate is being forced under either an oceanic plate or a continental plate. Mid-ocean ridges are areas along a divergent plate boundary where two oceanic plates are being pulled apart. This creates a thin ridge at the top of the boundary. Rocks just underneath the crest of this ridge are melted by upwelling mantle heat in a process known as partial melting. Partial melting is a process in which only a fraction of the material is melted. This results in a liquid portion as well as a solid portion. The liquid is less dense than the solid and then can therefore travel up through the solid towards the surface. The upwelling of heat in these areas is continuous, and some can be as old as 100 million years old or older. So in these chambers, just below the ridge is where magma is stored, and these are located just a few kilometers beneath the crest. So in these chambers, some of the magma cools, which creates new seafloor, but not all of it. When the pressure builds high enough, the other magma is then forced through fractures and results in fissure eruptions onto the seafloor. This process culminates in the production of basaltic rocks, which cover over 65% of Earth's surface. Also, the heat and lava created from these underwater volcanoes results in one of the most interesting ecosystems on Earth. Organisms living here survive on sulfur ejected from these vents instead of sunlight. So oceanic magma is much more mafic than continental magma for three reasons. One, magma chambers are constantly being replenished, which keeps heat high, and it also keeps the magma in there from cooling. Second, magma rises rapidly through the thin oceanic crust, and it leaves it less time to cool before it reaches the surface. Finally, the oceanic crust is mafic, much like the magma. So contamination from the crust doesn't really affect the magma's chemical composition. The next area where magma forms is on volcanic arcs. These are areas where magma is created above subduction zones. The two types of volcanic arcs are island and continental. Unlike underwater volcanoes, the volcanoes at these arcs can produce dangerous eruptions onto the surface. The magma created here varies from mid-ocean ridge magma in that it can be much more intermediate felsic. Two examples of these arcs are in the Andes in South America, which is a continental arc, and the Marianas Islands in the Pacific, which is an island arc. Island arcs are created when an older, more dense oceanic plate is subducted under another oceanic plate, but it's younger and less dense. Hot water from the plate being subducted is released into the overlying plate, which lowers the melting temperature of the rocks in the mantle, And with their melting temperature lowered, they succumb to heat and pressure under the Earth to form magma. So, unlike mid ocean ridges where the plates are being pulled apart, in subduction zones, two plates are being pushed together. The crust is also thicker in this environment, and these factors make it much more difficult for the magma to rise and reach the surface. Due to this resistance, the magma has more time to cool and evolve, and this is why island arcs are dominated by mostly intermediate mafic magma. Continental arcs form much the same way as island arcs. The only difference is that instead of an ocean plate being subducted under another oceanic plate, it's subducted under a continental plate. This continental plate has a thick lid of continental crust on top, which the magma must travel through in order to reach the surface. The rising magma is contaminated by the felsic continental crust, and also due to the extra layer it has to travel through, there's more time for it to cool and further evolve to become more felsic. This is why continental arc magma is dominated by more intermediate felsic magma compared to island arc magma. The final area where magma forms is in hotspots. These are still very much a mystery to scientists because they occur in random locations not really associated with plate boundaries. Scientists believe these hotspots are created by thermal upwelling under the mantle from deep in Earth's core. Heated material that's solid yet soft travels through the denser surrounding material and columns known as mantle plumes. When these mantle plumes come in contact with the overlying lithosphere, they melt that material and create magma. There are two types of hotspots: oceanic, which occur under oceanic crusts, and continental, and these occur under continental crusts. In the oceanic hotspots, magma only has to travel through the thin basaltic oceanic crust and therefore remains mostly mafic, but in continental hotspots, the magma must travel through that thick continental lid and becomes felsic in the process. So that's similar to in continental arcs. As the plate above the mantle plume, At the plate above the mantle plume, new volcanoes are created and old ones become dormant. This is evident in places like Hawaii, where there is a long chain of islands lining the path of the plate over the plume. This can give us some idea of the motions of the plate as we can sort of look at the shape of the arc of the islands above it. So to summarize, mid-ocean ridges create mafic magma. Oceanic subduction zones create island arcs with intermediate mafic magma. Continental subduction zones create volcanic arcs with intermediate felsic magma. Oceanic hotspots create mafic magma, and continental hotspots create intermediate felsic magma. So now let's look at some examples. This is the Mid-Atlantic Ridge. It's an example of a mid-ocean ridge and is the result of a divergent boundary between both the Eurasian and North American plates and the African and South American plates. These are the Marianas Islands. They're an example of an island arc. They're formed when the Pacific Island was subducted under the Mariana Plate. This is the Andes Mountains. They're an example of a volcanic arc and were formed when a number of oceanic plates were subducted under the South American Plate. And finally, this is Hawaii. It's an example of an oceanic hotspot, and it was formed by a mantle plume on the Pacific Plate.